Hi and welcome to this Leaving Cert Applied Maths video. We're looking at impacts and collisions, and specifically in this video we're going to look at type 3, which are oblique collisions. We're going to look at impacts and collisions for the new Applied Maths course, which will first be examined in June 2023. Underneath impacts and collisions, we have three different types that we want to explore. Type 1 are going to be impacts or single body collisions, type 2, which are direct collisions, and type 3, which this video is covering, oblique collisions. If you want to revise any of the type 1 or type 2s, you can use the videos linked in the description below.
Collisions. So in an oblique collision, the particles collide at angles to each other. We're going to use, just like before, Newton's law of restitution and the principle of conservation of momentum. So we're going to encounter two types of oblique collisions. The first one is where the y-axis is along the center of impact, and then the j remains unchanged, so only the I component changes. Where the j-axis is along the lines of center, then the I component velocity remains unchanged, i.e. only the j component changes. So we can be asked about energy as well. So these formulas are on page 55. We have potential energy and kinetic energy. And I would suggest a table like this, or something similar to use in each of the questions, just so it's really clear to see what we have and what we need. So just quickly to talk about vector versus scalar quantities. We have a section here coming from our log tables, and we have momentum. We're talking about Newton's experimental law, so that is using vector quantities, the conservation of momentum again using vector quantities. An impulse is a vector quantity. So that is, you can just use the I or the j component, whichever has changed. Energy is different. We're going to need the scalar here. So for example, kinetic energy requires speed. So that V stands for speed. What I find helpful to do is to actually put a little vector arrow on top of anything that is a vector. So like the I for impulse, I'll put it in like this. And it's a good way to kind of remind yourself what is vector and what's scalar. So we're going to cover 4 different questions in this video, and the first one is the 2019 question 5 part B, then the 2011 question 5 part B, then the 2016 question 5 part B, and then finally the 2010 question 5 part B. So the 2019 question 5 part B. A smooth sphere P of mass 2m collides with a smooth sphere Q of mass m. The velocity of P is 3ui plus 4uj, and the velocity of Q is minus 4ui plus 3uj, where I is along the center. I is along the line of the centers of impact. So that's telling us something really important. That's telling us that when they bounce, it's only the I's that are going to change. The coefficient of restitution is 5/7, and find firstly, in terms of u, the speed of each sphere after the collision, and 2, the angle between the directions of P and Q after the collision. So I'm going to set up my table here. We have P and Q. So I'm going to just change this to particle P and particle Q. So let's fill in what we know. Before, this is 3ui plus 4uj. That is a mass 2m. Q is minus 4ui plus 3uj, and it is mass m. We know that only the I components are going to change and the j's will stay the same. So let's say that this is, I'm going to call it x I plus 4uj. And then for particle Q, I'm going to call that y I plus 3uj. We know that our E is 5/7. That's useful to have pulled out. So now we're going to go and do Newton's law of restitution, which is V1 minus V2 is equal to minus E U1 minus U2. Now when we come to this, we're only going to put in the bit of the vector, so either the I or j that has changed. So for us, we're only putting in the I component. So we have x minus y is equal to minus 5 over 7, 3u minus 4u. So that is 7x minus 7y is equal to, so we have 3u plus 4u, that's 7u, so minus 35u. We can simplify that, divide across by 7, x minus y equals minus 5u. So that becomes equation 1. Second thing we're going to do is the principal conservation of momentum. So that's our formula here. Again, this is vector, so we're only going to put in the part that's changed. So we have 2m times 3u plus m times minus 4u. Because they're vectors, we need our signs. Then we have 2m times x plus m times y. And our m's are going to cancel out across, and we get 2x plus y is equal to, so we have 6u minus 4u, so that gives us 2u, and that is equation 2. So let's take our two equations. We have x minus y is equal to minus 5u, 2x plus y is equal to 2u. The y's will eliminate, so we get 3x is equal to minus 3u, so x is equal to minus u. Okay, so that first of all tells us that the velocity of p is going to be minus ui plus 4uj. So I have to go back to my equation. It doesn't matter which one I go to. I'm going to go to 1. And I have minus u minus y is equal to minus 5u. Minus y then is equal to minus 4u. So y is equal to 4u. So the velocity of q after impact will be 4ui plus 3uj. So now that we have both velocities, we're actually looking for the speed. So the speed of p will be the square root of minus 1 squared, 4 squared. So that's going to be root 17u. And the speed of q will be, and that works out just as 5u. And so there's our y, and these are our two speeds. So this is all part I. So now let's look at part 2. So we have the same table as before. This should be P and this should be Q. We have before and after filled in correctly, and we just have a little diagram here below which shows now the deflection. So we can see that P is going to go off to the left and Q is going to go off to the right. We know this because we've just worked out the vector of after for each. So part 2 asks us for the angle between the directions of P and Q. So to understand the angle, we actually need to bring these paths back, and we need to understand, oh, I shouldn't put that sign in there, apologies. We need to understand this angle here. So in order to do that, we have kind of two different ways we can work it. I think the easiest way is to work out this angle here and work out this angle here, and then the green angle will be these two taken away from 180. So to work out the angle of any vector, we should know that the tan of the angle is the j component over the I component, and we always take it as positive, so we get the acute angle. Okay, so I'm going to call this angle A, I'm going to call this angle B. So actually I'll change that, just the generalized one, to theta. And we have, okay, so the tan of A is the j component over the I component. So that's 3u all over 4u, so that u's cancel. So a is going to be tan inverse of 3 over 4. And we want to make sure when you're putting that into the calculator that you're working in degrees. And rounding that to 2 decimal places, 36.87 degrees. We also then want to work out tan of the second angle, which is b. Now remember, we're taking only the positive, so j over the I. These cancel, so we have just 4. So b is equal to the tan inverse of 4. And when we do that, we get 75.96 degrees. So then the angle between them is going to be 180 minus 75.96 minus 36.87, and that gives us 67.17 degrees, and that's our answer. So that was a lovely question. So that was really just to ease us into how we do these. Very, very straightforward, nothing very tricky about it. Really nice question. So 2011 question 5 part B. A smooth sphere A of mass m moving with speed u collides with an identical smooth sphere B which is at rest. The direction of motion of A before and after the impact make angles alpha and beta respectively with the line of centers at the instant of impact. The coefficient of restitution between the spheres is E. So part 1, if tan of alpha is equal to k tan beta, find k in terms of E. So regardless of what they ask in these questions, we always start the same. We're going to start with our table. Now, filling in what we know about our table, they're identical spheres. They both have mass m. B is at rest, so that's nice and easy to add in. 0i plus 0j. We know that the I part will change, the j bit won't. But before I do any of that, I need to understand what is the velocity of A before the collision. They've told us that the speed is u, but they've also given us the angle. So this is going to be written as u cos alpha I plus u sine alpha j. And now we can come along and say I'm going to use x for this, y for this one. So xi, yi plus u sine alpha j. And that's going to be plus 0j. So we've had to resolve. They didn't just hand us the resolved vector in this question. But we are well used to resolving, so that shouldn't be an issue. Now I'm going to work first of all with Newton's law of restitution, which is V1 minus V2 is equal to minus E bracket U1 minus U2. So V1 is going to be X minus Y is equal to minus E times U cos alpha minus 0. So tidying that up, we get X minus Y is equal to minus EU cos alpha. Second thing, principal conservation of momentum. So m1 times u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Only putting in the piece of the vector, the component that changes, in this case the I component. So we get m times u cos alpha plus m times 0 is equal to m times x plus m times y. Our m's cancel and we're left with x plus y is equal to u cos alpha. And that gives us two equations, equation 1 and equation 2. So let's work with them. Equation 1, equation 2. We get x minus y is equal to minus EU cos alpha. X plus y is equal to u cos alpha. The y's eliminate and we get 2x is equal to, now u is common, so you can pull that out in front and you get 1 minus, sorry, have that, a u cos alpha is common, so you can pull that out in front and you're left with 1 minus e. So x is equal to, I'm going to just switch this around, 1 minus e over 2 u cos alpha. So let's take, I'm going to take equation 2 because it doesn't have an e, and I'm going to sub in for x. So if I want to find y is equal to u cos alpha minus, and x is 1 minus e u cos alpha. A bit short on space here, so I'll try my best not to get too crowded with this. So we want to work with this a little bit, so we want to put it all over 2, and if I want to put it over 2, I could put a 2 in front and a 2 underneath. I'm looking at that top line and I see that a u cos alpha is common, and then I get 2 minus 1 minus e. If you prefer, you can multiply it out, and that is 2 minus 1 plus e over 2 u cos alpha. Okay, so they are our x, so the I component for the velocity after for particle A, and y, which is the I component for the velocity after for B. So now tan of alpha and tan is equal to k tan of beta. Now we've done all this work, let's see how we can get to that. So just pulled in this table here again with the afters updated so we can work with it. But just to be aware, part I was 20 marks and you 15 marks having just worked out the velocity pieces after. So it's a great question for that, even if you're not sure what they're asking, that once you kind of go and do those first steps, you are a good chunk of the way through the question. So we want to find tan alpha is equal to k tan beta. So tan of beta, so if we take a look at beta up here in our diagram, so it's going here, so we can get the tan of that by looking at how it's moving afterwards. So we can use tan of theta is equal to the j component over the I component, ignoring signs, and we'll get the nice acute angle. So this gives us the tan of beta is equal to the j component, which is u sine alpha, all over the I component, which is not very nice, unfortunately, over 2 u cos alpha. However, the u's cancel and sine over cos gives us tan. Now, the 2 on the bottom line is a little bit of a pain, so if you want to multiply the bottom line by 2 and the top line by 2, I'll do this in a few steps, we get 2 sine alpha all over 1 minus e cos alpha. This piece here, sine divided by cos, is tan, so that's 2 all over 1 minus e tan of alpha. So we've got our little, nearly at our answer. So what we've just worked out is the tan of beta is equal to 2 all over 1 minus e tan of alpha, but they want it the other way around. So to get tan of alpha on our own, we'll divide both sides by what's in front. So we end up with 1 minus e over 2 tan of beta. So therefore k equals 1 minus e all over 2. And that last piece was 5 marks, so just to work with the tan. This j over the I bit, we see it a lot when we have projectiles in question 3, but it is very, very common here. So if it's not something you're familiar with, really do keep it in your mind as you're going through any of these questions. So part 2 then says, if the magnitude of the impulse imparted to each of the spheres during the collision is 7 over 8 mu cos alpha, find the value of E. So impulse, and I spoke about this earlier on, it is a vector quantity which is given as mv minus mu. And it's important to understand that if you take the two spheres, the impulse in one will be the opposite to the impulse on the other, because one is this loss of momentum while the other one gains that momentum, because there is a conservation of momentum. So you can use either that you want, but in this case it's easier to use particle B. And the reason to use particle B is because then I don't have to worry about is it positive, is it negative, because magnitude just means that it's going to take the positive value of that, so the actual size of it, so not taking the sign into account. I know that B definitely gains momentum because it started from rest. So I'm going to use B. If you use the other ones, you just have to be careful of your signs. So we have m, the velocity afterwards, is going to be 1 plus e over 2 u cos alpha minus m times, and that's 0. That all cancels out. So that is the impulse is simply the first piece there. And they've told us that m 1 plus e u cos alpha, put that all over 2 or part of it over 2, doesn't matter, and that's going to equal 7/8 mu cos alpha, and we're trying to find e. So the m's cancel, the u cancels, cos alpha cancels, and we have a nice little equation which is 1 plus e over 2 is the same as 7/8. So I'm going to cancel out the bottom a little bit and say that that's gone, and then that'll leave us with 4. Multiply both sides by 4. 4 plus 4e is equal to 7. So 4e is equal to 7 minus 4. So e is equal to 3/4. And that's the last 5 marks of that 25 mark Part B from 2011. So 2016, question 5b. Two identical smooth spheres, P and Q collide. The velocity of P after impact is 3i minus j, and the velocity of Q after impact is 3i plus j, where j is along the center of the spheres at impact. And they've clearly shown this to us in the diagram. So the last two questions that we've looked at, both of them have been along the centers have been along the I-axis, which means that the I part changes, but the j stays the same. Now we're going to have different. Here, the j part changes, the I stay the same. And if you actually look at the direction of the arrows, that should make sense. The I bit is staying the same, the j is changing. One was going down, now it's going up. The coefficient of restitution is 1/2. Find the velocity in terms of I and j of the two spheres before impact. So it's quite a mixed up little question, but same that we're used to, just in a different order. So let's start with our table. Again, I've used A and B, but we're talking actually that this is P and Q. So we only know the afters, so they're identical. So I'm going to say M and M. Doesn't really matter. 3i minus j, 2i plus j. So here, actually, the I bits didn't change. The j parts did. Now, I'm going to call that plus xj and this plus yj. So now what I'm going to do, as per usual, is I'm going to start with Newton's law of restitution. And we can fill that in. It's going to be it's going to look slightly different because we're used to filling in x's and y's for the after, not the before. So we end up with 3 minus 2 is equal to minus 1/2. Oh, I have the wrong ones in. Be careful. That's habit. The i's gone in and I should have been looking at the j's. So it's actually minus 1 is equal to minus 1/2 x minus y. So when we work that through, we get minus 2 equals minus x plus y. So I'm going to say x minus y is equal to 4, and that is equation 1. So principal conservation of momentum, we have m1, so we have m times u1, which is x, plus m2, which is m, u2 is y, is equal to m times v1 is minus 1, plus m times v2 is just 1. M's cancel out, and we have x plus y is equal to minus 1 plus 1, which is 0, and that is equation 2. So now we take our two little equations and we're going to work with them. So we get x minus y is equal to 4, x plus y equals 0. So the y's eliminate and we get 2x equals 4, so x equals 2. We'll sub it back into either equation, it doesn't matter. 2 minus y equals 4. Minus y is equal to 2, so y is equal to minus 2. So these want the velocities. So the velocity of P and the velocity of Q. Actually, because they're before, I'm going to call them U. So we'll have the initial velocity of P and the initial velocity of Q, and that is 3i plus 2j, and then Q is 2i minus 2j. And a quick look at the diagram, yeah, that seems to make sense. So that is the answer to part I. So everything is completely backwards in this question, yet method doesn't change. So you have 15 of your marks now for part I. So I've just pulled in our table here for part 2, and it says find the nearest degree, the angle through which the direction of motion of P has been deflected by the collision. So P was traveling like this, that was its path, and it is now traveling like this. So the angle of deflection is this one here, and we can call it theta. Now it may be easier to sketch this out. I'll move it over here actually, so we can understand it a little bit better. So this was my path, and now it's traveling like this. So what I'm going to do is I'm going to take what was effectively the before for P and the after for P and work out the respective angles. And the angle of deflection will then be a sum of these. Now this is not usually the case. We usually see it like more of a subtraction, but it's just the shape or the turn of this question. So although there are other methods out there with formula and things like that, I like to be able to really take any question and work with it. So let's look at, I'm going to call this A and I'm going to call this B. So the tan of A is P before, so that's the J part over the I part. So A is equal to tan inverse of 2/3, which I'm not going to work out for a second. Tan of beta, then we take its after, but again, I'm only taking positive. J over the I, which is 1/3. So beta is equal to tan inverse of 1/3. So theta is then going to be a sum of the tan inverse of 2/3 plus the tan inverse of 1/3. And I'm going to put that straight into the calculator now. And they want this correct to the nearest degree. And without messing around with decimals or anything like that, we get 52.125. But they wanted it to the nearest degree, so that is 52 degrees. And that was actually worth 10 marks. So a nice little question about the angle of deflection. So in this last example, we're going to see an inequality appear. And sometimes these can be quite scary because students often say, I just don't know where that inequality comes from. So with collisions, it's quite straightforward. We have two places where inequalities can come from. The first comes from the limits of E. So the fact that E must be between 0 and 1. The second one comes from the idea that the spheres might have to have different signs. So for example, if there was going to be a collision again, we'd need to understand about one sphere has more speed than the other, or it might be a case that they're heading in opposite directions, so one is positive, one is negative. So you may have to work that way. So now let's look at 2010. Question 5, part B. A smooth sphere of mass m moving with velocity 6i plus 2j collides with a smooth sphere of mass km moving with velocity 2i plus 4j on a smooth horizontal table. After the collision, the spheres move in parallel directions. Okay, so that's interesting. The coefficient of restitution between the spheres is E. It wants us to find E in terms of K, and then we can see part 2 is where the inequality comes in. So let's start with our table. So we have two particles. We have particle A and particle B. So A has 6i plus 2j, and it has mass m. And then we have 2i plus 4j, and that's mass km. The centers we can see from the diagram, and it's another question, so they haven't actually told us, but the centers are along the I-axis, which means the I part will change, but the j will stay the same. So I'm going to use x and y. So that's I plus 2j, and that's yi plus 4j. So now that I have that set up, I'm going to use Newton's law of restitution, which is V2 minus V1 is equal to minus E U1 minus U2. So we have x minus y is equal to, we don't know what E is, U1, which is 6 minus 2. So we get x minus y is equal to minus 4e, and that's equation 1. So then equation 2, the principal conservation of momentum. So m1 times u1 plus m2 times u2 is equal to m1 times v1 plus, that's going to be m times 6 plus km times 2 plus m times x plus, oh, I don't know what's going wrong with this here, plus km times y. So the m's cancel out, so we end up with 6 plus 2k is equal to x plus ky. So that becomes equation 2. So we want to find E in terms of k. And before we do that, we're going to try and work out, as per usual, x and y. So equation 1 and equation 2. Let's see what we can do with it. So we have x minus y is equal to minus 4e. And we have x plus ky is equal to 6 plus 2k. So we can do a bit of substitution, but I think elimination is just as easy. I'm going to change all my signs of the second equation, and we have minus y, 1 plus k, is equal to minus 4e minus 6 minus 2k. So y is equal to, I'm going to change plus, is going to be 4e plus 6 plus 2k all divided by 1 plus k. So that's y. And then I'm going to go equation 1. I think it's going to be slightly easier. And x will be equal to minus 4e plus y, which is equal to minus 4e plus 6 plus 2k all over 1 plus k. So I've just cleared the right hand side there just for a bit more space. We want common denominator here, so we end up with 1 plus k times minus 4e plus 4e plus 6 plus 2k all over 1 plus k. We want to clean that up a little bit, so we get minus 4e minus 4ke plus 4e plus 6 plus 2k all over 1 plus k. The 4e and the minus 4e cancel, which is nice, and we get 6 plus 2k minus 4ke all over 1 plus k. So now we know our I component for particle A and particle B after the collision. So now we need to try and understand, well, how are we going to work out E in terms of K? We've done everything that we usually do, but there's one extra piece of information that we haven't used, and that was the piece of information that told us that after the collision, the spheres move in parallel directions. So that means that the angles here and here are going to be the same. So we can call those angles, so figure out which particle is which. So that is A and that is B. So let's call that angle alpha and that angle beta. Now see how we go. So the tan of alpha is the J component over the I component. So that is X. So 6 plus 2k minus 4ke all over 1 plus k, but this is the main division line. So the tan of alpha is equal to 2 times 1 plus k. So dividing by a fraction, instead we multiply by its reciprocal. 6 plus 2k minus 4ke. And cleaning that up a little bit more, so 2 can go into the top and the bottom. We get 3 plus k minus 2ke. So just cleared that. So now let's work out the tan of beta. Again, it's the J over the I part. The I is 4e plus 6 plus 2k all over 1 plus k, but this is the main divide line. So we get tan of beta is equal to, can't divide by a fraction, instead I multiply by its reciprocal. So we get 4 times 1 plus k, 4e plus 6 plus 2k. And I can divide the top and the bottom by 2, so 2 times 1 plus k all over 2e plus 3 plus k. So now we know that the tan of alpha should be equal to the tan of beta because they're parallel. So parallel means the angles are the same, but I don't need to work, well, I can't work out the angles, so tan is absolutely fine. So 1 plus k all over 3 plus k minus 2ke is equal to 2 times 1 plus k all over 2e plus 3 plus k. I'm going to divide both sides by 1 plus k, and then I'm going to flip my fractions. So I get 3 plus k minus 2ke is equal to 2e plus 3 plus k all over 2. Now just a bit of space so we can work. So multiply both sides by 2, we get 6 plus 2k minus 4ke is equal to 2e plus 3 plus k. We're trying to isolate e in terms of k, so let's move all the e's to one side. So we get 6 plus 2k minus 3 minus k is equal to 2e plus 4ke. Cleaning this up a bit, we get k plus 3 is equal to, I'm going to take out the e, so that's 2 plus 4k. So e is going to be k plus 3 all over 2 plus 4k. or any version of that you have. If your top line is mixed up, your bottom line is mixed up, that's absolutely perfect. So that's our answer for part I. And that was a lot of work for our 15 marks. There was nothing terribly difficult, I suppose, but it was just there was quite a bit of algebra. So now let's look at part 2, is prove that k is greater than or equal to a third. So we've just worked out E. So based off what I said, we're more than likely going to be using this inequality here. So that is 0 is less than or equal to k plus 3 over 2 plus 4k is less than or equal to 1. Now, if I use the one with 0, multiplying both sides by the denominator, we get k plus 3 is greater than or equal to 0. It doesn't really do much to help us. So I'm going to use 1. So it's going to be less than or equal to 1. So multiplying, well, we have to be careful here. So let me pull it out and then I'll talk a little bit about it. So we have an inequality. We don't at this point know if k is positive or negative, or do we? So you have to go and look in the question and say, well, what does k mean? So k comes from the idea of mass, so km, so k must be a positive number, so that's great. That means that we can do our multiplication without worrying too much about it, because 2 plus 4k is definitely positive. So that gives us k plus 3 is less than or equal to 2 plus 4k. Rearranging that, 1 is less than or equal to 3k. I'm going to flip it, so 3k is greater than or equal to 1, so k is greater than or equal to a third QED, and that is your last 10 marks, which was nice. Unfortunately, you wouldn't have been able to get them if you hadn't got your part 1 to some place for having an E. But it's nice and simple. Sometimes those inequalities, they can scare us, but actually lovely and straightforward.